All right. So, we started chapter 3 last time. We've been talking about processes. Now we're going to get into some of the more detail aspects of these guys after we talked about our virtual machine stuff last time. So, I think I had mentioned, well, I know I've mentioned last couple of classes, I wanted to start thinking about processes in terms of data structures, in terms of the object that as a programmer we might create to represent the details we have to remember about a process. Okay, so as a starting point here, here's our process, concept. So processes are our data structure representation of a program on various operating systems, and as we've mentioned, operating systems come in a different, some different flavors, right? So, for instance, what would be the difference between a server class operating system and a consumer operating system? So, Windows 2010 server versus or 2013 server, let's say, and Windows 7 consumer. What would be the differences in those operating systems, based on what we've talked about in here so far? Would have been a good quiz question, yeah.
The server version is optimized for multiple users, while the consumer one is optimized for a single user.
Okay, true. So what does it mean to be optimized? So what decisions might the server version make different from the consumer version?
The server version would divvy up the computer's resources a little better than, like a lot better than the consumer one, where the consumer one is going to just use all of the resources that it can for the user to use.
Okay, so not necessarily do it a lot better, it would do it more appropriately for that problem. Yeah, so share resources. The server one's it has to decide that I'm gonna share resources among more people. I'm not just trying to make one user happy, I'm trying to make a bunch of users happy. Where the consumer one can say, okay, well, I just need to make one dude happy and everybody else can, can go away, no big deal. Okay, so we have some different decisions. So with that in mind, we want to think about what impact that might have on our data structures. Okay, whether it has an impact or doesn't. Do we have to remember the same crap about a process, whether we are writing it for implementing a server class operating system or a user class operating system, or is the real difference just how we tweak a couple of variables? Does the server class versus the consumer class just change a couple of values? All right, so our textbook uses this term called job and process. I think I've even mentioned this before interchangeably. So a job is a process that's actually running on the CPU. A process is in the line to go onto the CPU. So let's just say they're synonyms with each other. It doesn't really matter. Process, program and execution, whatever. So a process at the beginning, let's say, is going to, so this is if we were writing an object for our process, we might say these are the properties, these are the attributes that we need to keep track of in order for our process to work. Okay, we're going to keep track of a program counter. We're going to keep track of a stack. We'll see what that might be used for in a little bit. And we'll keep track of a data section. What do you suspect is in the data section? Probably, well, true. But among those things, what do you think at the very least is going to be in there? When I give you guys programming assignments in other classes, well, what are you writing? A bunch of code, and that code turns into what? Turns into more code, right? So your high-level language like Java or Swift, whatever, ends up turning into a low-level language, assembler language. So a whole bunch of individual instructions, right? Magic trick 1, magic trick 2, magic trick 3, so on and so forth. So somewhere inside of this process data structure, we have to hold our code. Tell me the magic tricks in the right order of what I need to do. What do you think? What do you suspect that program counter's for?
Program efficiency.
Okay, well, so How does it help with efficiency? What is the counter to begin with? Well, when you count, what does a counter typically mean to you? Counts how many times it runs? Okay.
Or the number of lines that it goes through.
So now we're getting probably a little closer. Again, let's think about this. This is our data structure for representing a process, and a process is a program in execution. So if I have this list of magic tricks that I want the CPU to do, every single time this guy gets 5 milliseconds of CPU time, do I start over?
Keep track of it.
Yeah, I got to keep track of where I left off. I don't want to do magic tricks more than once. I want to do the magic tricks in an order. So a program counter is going to tell me where I left off. The number of instructions I've already executed, the line I need to start from, that kind of stuff. Make sense? Okay. So let's go a little bit deeper into that process data structure. All right, so our program code, which might also be called the text section. Okay, this guy's going to have, or we can say data section as well. So data section, text section, these guys are all kind of in one big group. So that's kind of what you were alluding to, saying that it's kind of all the stuff our program needs to execute. All right, so our code, as assembly line instructions, might be in the text section. Then we have the program counter. Now, all this other stuff over here, things like process registers, what do you think those are for? Why do we need to remember the process registers in our process data structure? What is a register, first of all? Probably made an appearance on a recent quiz. What's a hardware register, a processor register? Memory location, I've kind of advertised it as kind of a variable built in hardware. So it's a little tiny bucket of memory. Super, 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 super fast, right next to the CPU, right? So we could probably extrapolate, I think we've said it, but that probably the CPU uses these guys first when it can, because they're really quick. And when we think about stuff executing on the CPU, we want to keep things as self-contained as we possibly can so they're fast. All right, we certainly think of our CPU as being kind of the sports car aspect of our computer. If you're in modern computers, if your CPU is your bottleneck, probably time for a new computer. Okay, that's the punchline. All right. So I think I've mentioned in here that CPUs typically sit idle for 95% of the time, 98% of the time, somewhere in that. Most of the time, your CPU is doing squat. All right. So the second that your CPU becomes the bottleneck, when it's not fast enough to keep track, to keep up with the workload you're giving it, probably time to get a new computer. That's the time when your computer is truly antiquated. All right. Before that, you can probably fix most of your sluggishness problems with more memory, faster hard drives, that kind of stuff. Okay, so why might we need to keep track of the current state of those registers inside of our process data structure? Again, keep in mind, process data structure is how we represent in our operating system. It's the object that allows us to represent what a process is. And a process, as it said on the previous screen, is a program in execution. It's a job. It's something that's you've double-clicked on Word and it's running on your computer. Why do I need to keep track of the processor registers?
Except for the process itself.
Well, the processor has those registers. Isn't he the one who's using them? Isn't the processor like Pac-Man? I've done my Pac-Man imitation, haven't I?
Yeah.
I did, right? All right, so we won't do it again then. Okay.
Copyright infringement.
Copyright. That would be hilarious. Wouldn't that be evidence that it was really done well? If I actually got flagged for copyright infringement for too good of a Pac-Man imitation, then I have to have the whole. I have to contact Google and suggest that I didn't actually infringe. That was all me. It's just that good. Okay. So what's this? Yeah, exactly. So the CPU is using those registers. When would the CPU use those registers? When a process is running? Under what circumstances might it use those registers? Are they just there for show? I mean, we've said they're kind of like hardware variables. Kind of hardware variables, kind of hardware variables, kind of hardware variables, 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 variables.
Use a variable.
Yeah. Okay. So, and the CPU, we could think of it as kind of being Pac-Man eating lines of code, right? All right. This is the ABBA. All right. So he's eating these lines of code, and as the lines of code instruct the CPU to perform certain magic tricks, some of those magic tricks are going to require the CPU to kind of throw some data into these different registers, right? Okay, so now we have things stored in these hardware registers on the CPU. Why does the process data structure need to remember that crap? Why does he need to know what those processor registers look like?
Where you left off.
Those when he left off.
You might guess it.
Because what are the chances, generally speaking? I'm just asking you to come up with a pie in the sky number. But do you think that processes, when they first get onto the CPU, often get to finish their entire task on that one trip through the CPU? Okay, it's kind of like having to go through a car wash a whole bunch of times till you finally get the car completely clean. All right. So the process gets into the CPU. He gets some amount of CPU time appropriate for the goals of that operating system, right? Okay, and then he gets kicked off the CPU. Now, I probably mentioned the phrase already, but we're going to talk a lot about this idea of context switching. Have I talked about that yet? I kind of remember asking you like 2 or 3 times if I've talked about that yet.
The phrase is very
Okay, so context switching, again, we'll talk about it in a lot of detail, but it's the act of bringing a process onto the CPU and taking a process off of the CPU. That is, this guy who's leaving the CPU has to pack his bags, remember the current state of all the processor registers, things like that, so he can pick up where he left off next time. And then the dude who's coming onto the CPU has to unpack his bags, kind of like coming on into a hotel room, right? He has to unpack. How many of you actually unpack your bags in a hotel room?
I have.
You just like eat, don't you just eat out of your suitcase?
I have before.
Like if they give you a dresser, who uses it?
Yeah, that's what I'm saying.
Well, it depends how long you stay in the hotel room.
But even if you're there for a long time, like, don't really need to.
I mean, I kind of put, like, when I was traveling, I was in a hotel for like a week. So I put stuff
My
in the
wife
drawer.
will unpack our suitcases into those drawers if we're there for 5 minutes.
Drive me insane.
Unless you're there
We're
for
going
a
to
week.
Toma, Wisconsin tonight for some cranberry festival tomorrow. And so we're going to be in this hotel for 15, 20 minutes. Guarantee those drawers are going to be filled.
Going to Toma?
Yeah, I'm picking cranberries tomorrow morning, apparently.
That's gonna
I
be
get to
cold.
put on the wading boots.
They make them in your size?
I don't know. All I know, I'm signed up. My wife told me I'm taking her to Toma.
They might want to steal you as an individual because they'll just have you roll around.
Crush the cranberries.
Yeah,
Yeah.
they'll put you in a poncho.
built-in juicer. That's right. And you're still coming to my house tomorrow morning and chaining yourself up and he's feeding my cats. That's a euphemism.
Oh, I thought so. Is your cat okay now?
She's better. We have to wait till next week for them to do the follow-up, but they determined she had E. coli in her anal glands, and the systemic antibiotic wasn't actually getting into the anal glands. So we had to take her in, and they had to put the antibiotic directly into said anal glands. She did not like that. She was not a fan of that procedure. But
So they didn't knock her out or anything?
no, I held her
Oh my
while they're doing. Oh, she did not like that.
wow.
Yeah.
You got really clawed up?
Did I?
Yeah.
No, my cat would never do that to me. She claws everybody else. She bites and she hisses.
She knows better or because she loves you?
That cat worships the ground I walk on. She's so mean to everybody else. She doesn't do anything to me. Like Nick's been over, she'll just hiss at him. And I'll just walk right up, and she's like, "Oh yeah, I love this." Something wrong with her. She's unstable. But yeah, so the working theory is that they got the stuff in the right where it's at and should be fixed. So, but she's lost tons of weight. She's not even that fat anymore. Now she's just kind of mildly obese.
She's going to start.
She's like 12 and a half pounds now.
She's going to start thinking of you differently.
Well, I would say most cats are like 7 to 9 pounds, something like that. So she used to weigh over 18. Her gut literally like dusts the floor. And she keeps going. It's awesome. Yeah.
Could she still like jump and perform everything?
Ish. Yeah, she's on because she's an old cat and she's elderly, so she's on chondroitin stuff. She takes these treats that are supposed to like make her joints hurt less because she's too fat for her knees. Do cats have knees?
Yes.
They're inverted, so is that still a knee? Yeah, so sometimes she has trouble. We have a king size bed. It's kind of high, so sometimes it's like she gets about 3/4 of the way up and has to climb, ripping the sheets as she's doing it. So, ish. I think it's a fair statement. Okay, so in any case, we need to remember the current state of our processor registers because a process might need to set the processor back to the state it was last in when it needs to pick up from where it left off. Okay, so that's a piece of information we need to remember, an attribute of a process that we need to keep track of. All right, so a stack containing temporary data, function parameters, return addresses, local variables, yada, 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 yada. As in our programming life, when have we run into the stack? I know we've created stacks for those of you who were in the 300 class, right? So we dealt with the stack data structure. But more than likely, when you're learning how to make a stack, you don't necessarily think about when would we need a stack. So those of you who are in 470, how are we really, really exercising the stack these days? And that's also a euphemism. Man. What is the stack data structure used in our operating systems? Well, besides the slide telling you that the process has one in it. Gives you a little hint here. It says function parameters, return addresses, local variables. Just randomly, just memory. Just use it for memory.
Somewhere in there, I'm sure.
Memory is probably, well, especially since this says local variables, which then gets stored in memory. How does recursion work? Okay, function calls itself, so that's what recursion is. How does it work? If you were implementing recursion, or for those of you who are in 470, when we implement recursion, probably a little bit after midterms or so, we actually write how recursion works. How do you suspect? So you say it's a function that calls itself, and we've kind of represented this idea that this function call has to wait for another version of itself to finish, right? What does this dude do while he's waiting?
It just stays at the bottom of the stack.
So he gets tossed onto the top of the stack to be returned to later while this next guy is at work. And what does the next guy do? Well, he might call himself recursively onto the top of the stack. So push the function onto the stack, push the function onto the stack. Once this top guy gets his answer, pop, 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 pop. We've resolved our value, right? So when you have bad recursion, that is infinite recursion, what's the error message you've gotten in Java before? Stack overflow error, right? Okay, stack overflow error. I put too much crap on the stack. All right? So it's not going to give us an infinite stack. Because if it gave us an infinite stack, it would be scary, right? Okay, especially if that stack, like it used to be, was controlled by the operating system. So instead of compartmentalizing it inside of a process where a single process could just destroy itself, rot away, if you will, we're going to put it at the operating system level in the old days. So now you have a single process that has written an infinite recursive loop, let's say, that keeps throwing copies of a procedure onto the stack never finishing. Now we can say that a procedure isn't that big, but probably a procedure weighs more than an int. And it's probably the difference between like an apple and like a shopping cart. All right, that kind of thing. Well, you could fit a lot of apples in Meyer. You could fit a lot of shopping carts in Meyer too. Less shopping carts than apples, but still a lot, right? So eventually that's going to add up. So in the old days, we used to have situations where our operating system would crash because of one rogue program that decided to eat up, doctor, all the memory. Eat up all the memory. So we'd be stuck in this situation, right? So now we've kind of compartmentalized things a little bit. We talked last time about this idea of a virtual machine as pros and cons, right? So we can almost think of this process data structure as in some ways solving some of those virtual machine problems, localizing the stack problem to the process. So the worst that happens is Microsoft Word crashes. It doesn't bring down the empire with it. Okay, that makes sense? All right, so stack is going to be used for, a stack is used even for our very first function call. So it's not just used for recursion, but if we use the stack to push the current function that's being called, we probably would use the stack to call recurring functions as well. All right, so that's that's the stack, process registers, data section. So this is kind of our global variables that might be used throughout the application, because keep in mind that text section probably gets a little bit more complex. When you get this giant list of magic tricks in the text section, imagine how that has evolved over the years from our early procedural languages that just have basically a single file with all your logic in it, to now we might have a program in an object-oriented language that has 30 different source code files, and they all have their own little magic tricks associated with them, and this guy calls this guy, who calls this guy, who calls this guy. So inside of this magic trick file, you have these jumps. It says jump from here over to here, jump from here over to here. So there's a lot of crap we're keeping track of. So this data section is dealing with some of these variables that are shared amongst those guys. And the modern approach to that is something called the singleton design pattern, which I'll probably talk about at some point. But in any case, some of these guys have gotten more and more complex over the years, which then forces us in modern operating systems to pay a little bit more attention to these data structures. Okay? Who would have thought data structures were this important? Probably none of us when we were taking 300, right? Kind of see how all these things start connecting back to each other. Yeah, it's amazing how your education actually is valuable. What are you going to do? All right, so the heap, which is a cool name for a priority queue, so a queue that stays in a certain order. Okay, so containing memory dynamically allocated during runtime. All right, so our heap, we could almost, for those of you who are in 470 right now, think of it as at least a player involved in our variable environments, right? So it's a priority queue, so the most local stuff needs to kind of float at the top so we can access it quickly, right? But the other stuff still needs to be there, all right? So we use a heap for that type of thing. We use a stack for holding our procedure crap. So we can think of variables in the heap. Stack is our procedures, which can internally contain variables. So you could even say that a procedure itself might utilize the heap. So a procedure has local variables, and where does it keep those local variables? During runtime, it's working with them out of the heap. Okay? Something like that. All right, so, they're saying, okay, so program is a passive entity. So a program is Microsoft Word living on your hard drive. A process is formed when you double click, okay, and it launches into memory. This actual process data structure is created, blah, blah, blah. So there's our GUI mouse click thing or command line entry. However we launch it, there's going to be this loader that loads it from hard drive into memory, and the process is birthed, is created. I like that word, birthed. Sounds very creepy when I say it. Like that. Really? I've missed you at Bible study lately. What's up?
I work.
Really? Is that more important than free lunch? God and grub? Just racking up the
God
Christian.
would come first.
Well, I mean, I said God and grub.
You said free lunch first.
Well, and then I amended. Just terrible. Just heathenistic, really. So let me get racking up Christian worldview points here, people. That's it. Infinite recursion. Stack Overflow. All right. So, one program can be several processes. How might that happen? How might one program become several processes? We've mentioned it in here, and we probably laughed during this conversation. Yeah, we fork children. Okay, so when a process forks copies of itself, and when a process forks copies of itself, we get new processes. New processes are birthed. Okay? Oh, yeah. Love that. Okay? New processes are birthed out of that, creating these monster things, these data structures that are keeping track of all this crap. That's a copy of everything. So we have this 10,000 line program, this process that's sitting here that solves all the world's problems, obviously, right? Okay? So it solves all the world's problems. And then we decide, you know what? I need to do this one little piece, these 15 lines, but I want to do it in the background. Okay? I want to do this asynchronously. We're going to be talking about asynchronous stuff at some point. But, I want this program to be able to keep going while this little part can do its job in the background. Okay? So what do? Well, we fork this guy into two copies. All right? And then the copies now know, they don't know who the real is. They don't know who the clone is. Okay, so they have to ask themselves, what is my process ID? Okay, so I was a process, and one of the things that's left out here so far is this idea of a unique identifier for a process. So generically, a process is the stuff we've talked about here, but we have to have some way at the operating system level of uniquely identifying these processes. Make sense? All right, so when this process hits the magic trick that says, call the fork system call, and the operating system says, okay, you got it, boom! And all of a sudden the process goes into two processes. Oh, you see these special effects? This is awesome stuff. Brought to you by Nabisco. All right, so it's one of those days. Yeah. Okay, so in any case, we split into two processes. Identical in every way. Then each process is looking at each other. All right, which one of us is the clone? We're not sure. All right. So they have to ask themselves, what's my process ID? What's the process ID? Because the fork system call returns a process ID. So one of those guys will receive a 0. Like, oh, I'm the original. Okay, I'm the original. Okay, the other guy's going to get this new process ID. It's like, I'm the clone. So now we just have an if statement. If I'm the original, keep doing my old crap. If I'm the new guy, do these 15 lines. Even though I'm surrounded by 10,000 lines of code. And the previous copy of all the registers, and the current state of the heap, and the current stack. Okay, there's a giant monster to do these little 15 lines of code. So certainly, Doc, memory inefficient, right? So we just created a monster to do something relatively small, just so we can have our original program not get blocked. So non-blocking execution. So now, instead of having one process that has to stop and wait for these 15 lines to finish, maybe those 15 lines take 5 minutes. Maybe it's doing some sort of system backup or something like that. So rather than waiting for those to finish to be able to continue on, we fork a process and have that guy do that stuff in his own CPU time and his own stuff. Because remember, the CPU, we're leveraging the operating system again here. The CPU scheduler, this guy is going to make sure this process gets a little CPU time and this process gets a little CPU time and so on and so forth, okay? So we're going to go ahead and we're going to just put the problem on the operating system and say, hey, I need this crap to happen in the background. I don't want it to stall my program here, so I'm going to spawn a clone of myself. I want you to take care of him. All right, so you got this giant monster, and even every time he gets onto the CPU, he's unloading all this stuff, and he's this giant bulky data structure, and he's only doing these little pieces, these couple of lines right here. All right, and they probably deal with a whole lot of I/O, so it's extra CPU inefficient, right? So he might get 5 milliseconds of CPU time, But after, a quarter of 1 millisecond, he says, oh, I need to do some I/O. I just unpacked my bags. I've only been on the CPU for 5 minutes. I'm like the Littman's traveling. Okay? So, anyways, unpacked his bags, repacks them, goes into the wait queue for the I/O, blah, blah, blah. Back to the races. On top of that, what other problems? So, we've replaced processes with a new solution, but let's try to explore the problems that forking a process causes. Why is this potentially bad for the health of an operating system? Why is forking a process potentially bad for the health of an operating system besides the inefficient use of memory?
Would they be trying to use the same resources mapped exactly the same?
Well, maybe don't even take it that far. Would you say that every single process that lives on the operating system is at the very least competing for the same resources on the computer?
Yeah.
So the more processes, the more competition? What would keep me from writing a program that just had a for loop that went through 1 million times and literally forked a new child process each time through? New copy myself. Anything keep me from doing that?
Hopefully, a safeguarding operating system would prevent you from doing
Yeah, it's called the power button. Yep. Okay.
Well, I mean, there has to be something, otherwise. Why is it-
Certainly, as we started looking at that problem, right? How do we fix that problem? But generically speaking, couple lines of code. I can just spawn. I could write a program whose job it is to spawn off copies of himself. What does each copy of him do? Spawns off copies of himself. All of a sudden, you have you have to get that rabbit birth rate, right? Aren't rabbits the ones that reproduce really quick? Yeah, you get that, all right, on our operating systems. So now, instead of having 15 or 20 processes all vying for the same system resources, we have 40 million processes in this, within a couple of seconds that are, exponentially spawning more, to the point that now our operating system, it feels like it's in gridlock. Nothing is getting enough CPU time to accomplish anything because these thresholds that, the Microsoft people or the Apple people put into the operating system for realistic circumstances, like, oh, you got 25 programs running on your computer. Some of them are legitimate programs we see running in the foreground, but other things are like little system backups and stuff like that. So we can believe that there's 25 things kind of happening at the same time on our computer. It's not mind-blowing. Now we got this guy who has 40 million. Didn't really take that in consideration when I did my threshold math. All right, so problematic, correct? All right, so the idea is that processes could be potentially unhealthy for our operating system because we're taking advantage of what we know about our operating system. So as like a hacker or cracker or whatever the bad word for the people who write viruses and crap like that today is.
Their name is 4chan.
Huh?
I believe their name is 4chan.
Oh, is it?
CNN, when a member from 4chan, did, hack the PSN network.
Okay.
CNN came out and said the hacker known as 4chan.
Oh, okay.
Responsible.
Gotcha. A long time ago, there was hackers would argue that, well, if you're a hacker, you're actually not malicious. The crackers are malicious.
That's just racist.
Yeah, I think that's what happened. I think then people started using cracker differently, right? So then now we don't even know what to call ourselves. Right. So it's are we the Autobots or the Decepticons? Maybe that's what we should call them. The good guys are the Autobots, right?
It actually sounds pretty good. Autobots and Decepticons, it works.
Yeah, we just started this trend.
Hackers use
Started on
automated bots
Yeah,
all the time.
yeah.
So that's perfect.
Speaking of that, why did Decepticon leader guy?
Megatron.
Megatron. Why did the original Megatron turned into a gun?
Yeah.
It's so stupid.
Kidding me? You see how big the gun was?
But how you're not even self-sufficient? One of your minions has to use it.
Wasn't it the idea like they came together to create a bigger thing too?
I think so. Yeah. We used to be big in the Transformers. We had the original Optimus Prime. You know, I guess they're worth a whole lot of money now if you have them like in a sealed thing. I mean, I think my brother once hit me over the head with one. I had to get stitches. Yeah, so we didn't take good care of it. is the punchline. But yeah, we always thought it was stupid. And then the gun, it never really stayed together very well. It was like this really flimsy gun because you still had kind of an arm hanging out of the side, right? Just dumb. All right. So, in any case, for a Decepticon to write a program that creates a lot of processes in perpetuity, and if they want to make this quicker, they can fork and have each one fill in stacks with stuff because that'll get fun, right? So, in any case, it could really harm the operating system because we're taking advantage of the operating system's features to pull some of this stuff off.
Is there a way to interrupt that if it happens?
Well, I mean, I'm sure somewhere in there was, as our operating systems evolved and this started becoming problems, maybe we put some sort of limit on how many times an individual process can call the fork system command. Like we had our picture up here that showed that layer of those system commands that have to sit there. So before you're allowed to use the fork system command, you have to go through some sort of process, right? Some sort of maybe, like trying to use a visa to get back into the country, that kind of thing. So maybe we say, you know what, you've kind of, passport, right? Yeah. We've kind of used, you've kind of made the fork system call a lot recently. Maybe hold off. Something like that. So
this is bringing to mind our Rickroll again, spawning.
Yeah.
Killing the game.
That's right. So good. So good. All right. So in any case, our more modern approach to this is called a thread, where now a process spawns off microprocesses within themselves called threads, which only have the pieces of information in it that they only has those 15 lines of code, for example, and it's sharing the CPU time with the process. So if you want to spawn off 4 million threads, you're only hurting yourself. All right, kind of the punchline there. All right, so this is what a process might look like in memory. So this is our data structure. We're gonna, so once we're in memory, we have our stack, which is kind of elastic. We have our heap, which is kind of elastic. So we might have stack and heap space in our modern process data structure shared. So these guys might share the same memory, where on one side of it, kind of the top of the stack, is the bottom of the heap. And they feed off of that in a stack type fashion. Because really, stacks and heaps are the same kind of data structure, right? They're both linear linked data structures. But stacks, we push things onto the top, we pop things off of the top. So the way we interact with a stack is just different than the way we interact with a heap, which is how we'd interact with a queue. Okay, a queue is first come, first serve. So we remove from the front of the line, we put at the back of the line. Heap adds one more layer in there and says, sometimes what we just put at the back of the line gets cut in line. Because sometimes things are more important than other things. Something like that. Okay? Then we have our data section and we have our text section, and these guys kind of share the same space as well. All right, so this here would be the amount of memory that a process might take. And this would be an operating system decision. So what is the maximum size we will let a process be? Well, that maximum size has multiple ramifications. So when Apple or Microsoft, when they decide what the maximum size of a process is, what does that mean? What does that imply? What are the negative side effects, or even just the side effects of that decision?
Every process that any application that has to have their processes be below that amount.
Oh, it's when we spawn off a process data structure, when we create an instance of that guy, that's how big it is. So they can say, well, what's the maximum size of a process? Well, let's just say a maximum size of a process is 1 megabyte. Be a pretty big process. They're smaller than that, but let's just say that's it. So now, 1,024 processes takes up a gig of RAM. And when you start adding up, 1,024 processes doesn't seem like that many processes. Realistically, we probably don't have 1,024 on average running on our computer, but it wouldn't take a whole lot to have 1,024 running. Especially if we had these old rogue processes that didn't die off easily. That was the problem with kind of the Android operating system. You'd have every application you ever launched would still be running as a process. In the virtual machine, it's still a process, and it had a size associated with it. So eventually your machine would become unusable. You had all these things taking up battery, so battery life was crap. And then eventually you just had to restart your Android device because you'd have too many things that other programs wouldn't be able to launch. Okay. It's just an operating system concept, not an Android is bad type concept. So, if we make the process data structure too large, we can't have as many of them. If we make it too small, now we're limiting the abilities of our processes. We have Stack Overflow error, for example. Stack Overflow error doesn't mean that we ran out of memory in our computer. It means we ran out of space in our shared stack heap space for this process. Make sense? We only get so much.
So does that error get thrown before the process is actually created, or the process is created and then we say you're too?
Well, the Stack Overflow, the easiest way to see that in Java is by just writing an infinite recursion. So you're only running inside of one process, and you're just throwing, a method data structure, which we'll also do in 470, function data structure. We're throwing that onto the stack over and over and over again, right? And that guy needs to keep track of the current parameters, current value, everything, blah, blah, blah.
Is that how memory leaks happen? It's just like a rogue recursion that someone can catch?
Memory leaks, well, I guess memory leaks is kind of a generic term, but generally speaking, we see them most often in like C and C++ applications where we have direct control over memory. But it can also happen in Java when there's a bug in the automatic garbage collection. So at the general level, a memory leak is memory that the program is no longer using, but that has been earmarked, that has not been removed from the operating system as memory that's available. Okay, where memory leaks can be harmful is when you have two programs that live close to each other in RAM. And this guy, so this is kind of, when we don't have virtual machines to protect them. So this guy is trying to access memory like in an array here and oversteps one bucket, let's say, and starts accessing memory from this other guy. That would be a memory leak. So this guy's leaking into the memory space of this guy because he hasn't gotten rid of this memory or has abused the. So in C, we can allocate 100 kilobytes of RAM for a buffer, let's say, or an array. So buffer, fancy operating system name for an array. And then if we start writing past the end of that to 200 kilobytes, now we have 100 kilobytes of leakage. I like that word too. That sounds kind of creepy. Okay, so 100 kilobytes of leakage. Well, in this case, it's memory leakage, but I guess you could take that wherever you want. But you're leaking past, so that's a memory leak. All right, so now that could possibly hurt another program because this other program might have their array right here, right next to it, and now your stuff is overwriting part of their stuff because you're leaking into their memory space. Make sense? So that's, I guess, generalistically what a memory leak typically is. All right, so this has to do with our process scheduler. So our process state deals with whether a process was just created, so it's new, just being birthed, whether it's currently running on the on the processor. So when it's in a running state, it has the CPU resource. Whether it's waiting, that is, the process is waiting for an event to occur. Usually, we think of waiting as being an I/O interrupt. So it's usually waiting on I/O stuff. All right. Ready means it's in line, getting ready for the CPU. So I'm not waiting on anything. I'm not waiting on any extra stuff. I'm just waiting for my turn on the CPU resource. Terminated would be when it is it's dying. It's done. Finished. All right. So again, same deal here, right? So this new process is admitted into the ready queue. Okay, and at some point we're going to probably want to replace the idea of a ready queue with maybe, although they never call it this, but a ready heap. Okay, because really this is a prioritized queue. So not all processes are created equal. So typically, as an end user in the operating system, we want our process that's in the foreground to have kind of special treatment, right? We want him to, if anybody's going to get extra CPU time, we want the one that we're currently working on to get extra CPU time. So sometimes when something comes into the ready queue, we want to give it a little extra love, something like that. All right. So ready queue gets into the CPU, so it's running. Two different ways it can get interrupted. One interrupt is when it finishes naturally. You've had your 5 milliseconds of CPU time, so we're going to cut you off, pack your bags, go back and get in line. All right? So this guy didn't get interrupted for I/O or something. Otherwise, we can have an I/O event wait. So this would be another kind of interrupt where we say, yeah, your time, you still have more time, but you're not doing anything, so we're going to kick you off because you need to go and wait for something to be able to continue. Once you're done waiting, you get back into the ready queue. And this goes through something called the scheduler dispatch. So something I've referenced several times up to this point is the process scheduler. Okay, so we have a computer program running on our operating system that's in charge of this crap. Make sense? Questions, comments, concerns, bribes? All right, we might have a quiz on Monday covering something we talked about today, but no homework this weekend. I don't get like a dance out of this or something? You do have 470 homework, right? Did you do that yet? It's completely impossible. I looked at it last night, I just started crying.
What? I thought, you're lying. It's not that hard. No? Okay, I didn't think so. You scared me for a second.
None of them are that hard.